Hello, y'all. Welcome to another video. This is on lesson 8, which is on exponents and polynomials. Well, mainly just exponents for this class here. This is part of a new module, and it should be a shorter module than the prior ones as well. I think the prior ones can be sent in a sense review, but like especially the systems of equations one was pretty like rough. So it's nice to go to a new module entirely that's talking about just like new stuff that students generally they don't struggle in as much. They struggle in the rules, but the actual problems are like once you understand the rules, they're not so bad. And it's about exponents, right? So what is an exponent? An exponent is usually in like that superscript form, like if you have the number or the letter x to like the fifth power, this is like your exponent. If you have some sort of base, you have to some power, it's called the exponent as well. These could be numbers too, like 5 to the fourth power. And what does that mean? It means multiply by that base, whatever your base is, the amount of times equal to that exponent. So if I have 5 to the fourth power, I'm going to multiply by 5 the amount of times that's equal to the exponent 4. Let's try that. 5 to the fourth power is I multiply by 5, the amount of times equal to the exponent 4. So I multiply by 5 4 times like that. So this was a 5 and this was a 4. That's how we do it. And there's some rules or like ways to do this immediately if you kind of know the rules of adding exponents and subtracting exponents and when you're multiplying by the same base and so on. We're going to start from like ground zero because this is how you can always do a problem if you just feel like, man, I don't really know the rules. I feel like I'm making small mistakes here because it's easy to make mistakes if you just use the rules. So I'm just gonna have a theme here, which is when in doubt, write it out. Because oftentimes students tend to just multiply these bases together in the wrong way, or because the rules have sometimes you're adding the exponents and sometimes you're multiplying the exponents, it can be tough to remember what you're supposed to do, and it's not really as intuitive. But so long as you know that a base to an exponent power means write out that amount of exponent times, then we can kind of like have a good solid foundation here. So what do I have in this first problem? I have a to the third times a to the second. What does that mean? Well, when in doubt, write it out. I have a times a times a times a times a, right? Because the second one is a to the second, the first one is a to the third. And together, how many do I have? One, two, three, four, five. That's a to the fifth. See, not too bad, right? If I have it as numbers as well, I can do the same thing. I have, let's go red again. 2 to the third, I have 2 to the eighth. So what's 2 to the third? 2 times 2 times 2. What's 2 to the eighth? That's annoying to write out, but when in doubt, write it out. 1, 2, 3, 4, 5, 6, 7, 8. Okay, well, how many twos do I have now? I have 3, 4, 5, 6, 7, 8, 9, 10, 11. So this, as a singular exponent, if I was combining these together, is 2 to the 11th power because I have 11 twos. So just like I can expand it, I can also move this all together to be one number to a power like this, right? Okay, what else do we have here? Oh, I have 5 to the third times 5 to the 8 times 5. All right, when in doubt, write it out. So I have 5 times 5 times 5 times, this is 1, 2, 3, 4, 5, 6, 7, 8. And then this last one is another 5. So how many is that? Well, if I counted them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 5 to the 12th. And this is the most like guaranteed, I guess, straightforward way to do this problem. If you know the rule, I don't mind writing the rule here. If I have, let's do any, uh, let's do like x as like a random variable to the a power times x to the b power. If you have the same base multiplying, We have the same base of x, but we're multiplying two exponents together. What do we get? We get x to the a plus b power. And let's check. We have the same base. We're multiplying these together. I have 3 plus 2 is 5. So I could have just done a to the 3 plus 2 power or a to the fifth. I didn't have to write it out, but it works when I write it out. For one like this, I have 2 to the 3 plus 8 power. Oh, that's 2 to the 11th. But it comes literally from this. Lastly, well, when I'm multiplying multiple of the same base like this, it's still the same idea. We could just like translate it from 2 to 3. So I see this is really a 5 to the 1 power. So I end up, when I combine it, 5 plus 8 plus 1, or or 3 plus 8 plus 1, which is 12 here. So we get the same answer as well. So it works for both ways. You can choose whatever you want for each of them. I think when in doubt, write it out works very well. It works especially for things like this, because if you're like, oh, let's just add these exponents together. So 3 plus 8, okay, that's 5 to the 11th power. Well, you forgot that 1 there, because we often don't put a 5 to the 1 power. We just leave it as 5. So because you can need to write it out always, if you do write it out always, you don't make those sorts of mistakes. So let's do this last one here. We have r plus s to the 7th and r plus s to the 6th. Well, you might be like, all right, I can just add these exponents together and get the answer. You don't have to write this down if you don't want to, but I'm going to. R plus s, 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 r plus s. 1, 2, 3, 4, 5, 6, and r plus s. And I'm actually gonna, since I'm on a iPad here, I can kind of cheat a little bit. I can just copy, paste, change my color to green. So I have, ooh, let's move this around like that. This is 7 r plus s's, and this is 6 r plus s's. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This ends up equaling r plus s to the 13th power. So my base was r plus s. It's okay for my base to be something ugly. It's okay for my base to be 3x plus 5 happy face, right? If it's to the 10th power, I write 3x plus 5 happy face 10 times out. That's what it means to have an exponent. Cool. Um, so when in doubt, write it out. Next sort of base idea we're going to work with is when we have fractions with exponents. What do we do? Well, again, all I know is to write it out when need to write it out. But in particular, all I know is if you have anything in a numerator and anything in a denominator, this equals 1. In particular, these cancel. That's good to know. That's just a over a. This is really a divided by a. I mean, what is 7 over 7? Or what is 7 divided by 7? That is the same thing. I know fractions are scary, but that is the same thing. That's just equal to 1, right? So the way we view this is like these two cancel out. If I had a times 5 here, these would cancel out. I'm left with 1 times 5, or 5, right? So that's what we're going to be doing, combined with, when in doubt, write it out. So what do I have here? I have on the numerator, a times a times a times a times a. In the denominator, I have a times a times a. And I only know one thing. I only know for fractions, when I have an a in the numerator, an a in the denominator, or something in the numerator and the same thing in the denominator, they cancel across multiplication. Cancel, cancel, cancel. I'm left with a times a in the numerator, or a squared. Nice. What about, let's do a to the third over a to the fifth. Let's go down this way. So again, I'm going to write it out. A times a times a over a times a times a times a times a. And these end up canceling, 2, 3. And I'm left with, well, there's nothing at the top. These all cancel. I still have like an imaginary 1 here. If I like cancel everything times 1, there's still a 1 at the top. So don't get scared that everything cancels on one side. On the denominator, I have two a's. So a times a becomes a squared. Not 2a. Remember, a times a means we have two of those, which means we have a 2 power for my exponent. There. Okay, it still works for numbers as well. 7 times 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 7, all divided by 4 sevens on the bottom. And what does this become? Cancel, 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 cancel. I have 5 sevens left. So 7 to the fifth power over 1. You can do it like that, right? Because I have, just like I said before, all these cancel. There's still a 1 in the denominator. But remember, fractions mean this divided by this. So 7 or to the fifth or any number divided by 1, that's just the same number. So this is just 7 to the fifth. You could just remember that. It's good to know. It still works for more complicated numbers as well, like this. Let's say I have, or not more complicated, but like exponents and numbers combined together, like this. So let's write this out. I have what? 4, and then I have times p times q times q times q times q times q times q times q. I know, a lot of writing. Yuck. But it still works. Divided by 6. And now I have 5p's here, and then times 1q here. So how do these things cancel? Well, they cancel by just this rule. Whenever you're dividing by the same thing, you can cancel that one thing. This cancels, and this cancels, and it looks like this cancels as well. Also, I have my 4/6 can cancel by like dividing by 2 on top and bottom, right? This can be reduced. 4/6 is the same as 2/3 because they both have common powers or common factors. So this is equal to 4 divided by 2 is 2 divided by 3. What am I left in the numerator? I have 1, 2, 3, 4, 5, 6 q's. And then I have 1, 2, 3 p's. And that's my answer there. So if you see what was going on, we do have a rule that is going on here. And that is if you have, how did I write it before? I said, okay, same base in fraction rule is when you have x to the a over x to the b. This ends up being x to the a minus b. You subtract the top exponent from the bottom exponent. So a minus b like this. So let's look at this. I have a to the fifth over a to the third. 5 minus 3, because I'm dividing with the same base, 5 minus 3 becomes a squared. Not bad. 7 to the ninth, 7 to the fourth. When I divide by something with the same base, but different exponents, I am subtracting those. 9 minus 4 becomes 7 to the fifth. That's how the rules end up working. It works for these as well. These are a little bit tougher to see, so we'll kind of get to, like, we'll continue on with the rules right now. Because what does it even mean to have a negative exponent? So let's kind of work through that here. Or even a 0 exponent as well. What is 3 to the 0 power, right? 3 to the 1, 3 to the 2, 3 to the 3. Let's see if we can see a pattern here. 3 to the negative 2, and 3 to the negative 3, like that. I guess I don't need that last number there. Okay, well, we already know what 3 to the 1 power is. That's just 3, so that's not too bad. I can get these positive exponents pretty well. When in doubt, write it out, right? 3 times 3, 3 times 3 times 3, because I'm multiplying by 3 times here, right? Okay, well, what is 3 to the 0? Let's see if we can recognize some patterns here. I see I am going up by multiply by 3 every time here. I start with 3, To go to the next column, I multiply by 3. To go to the next column, I multiply by 3. If I had 3 to the fourth, to go to the next column, I'd have multiply by 3 again to get another 3 to the fourth here. Okay, that's an interesting pattern. What if we start at the end of the table and go backwards? So going from here to here, it's like I got rid of a 3. Or in another way, it's like dividing by 3 here. And then going from here to here, I divided by 3. It's kind of like I took away a 3. So if I continue that pattern left, what happens? I divide by 3, and I end up with what? 1. Because 3 divided by 3 becomes 1. When I go to the next row, divide by 3, 3 divided by 3, 1/3, right? Next row, divide by 3. Oh, that's 1 over 3 times 3, because I'm dividing by 3 again. It's almost like I'm adding a 3 in a denominator or including a 3 in the denominator, like so. And then the last one, when I divide by 3, becomes 1 over 3 times 3 times 3 in the denominator. Going from here to here is the equivalent of dividing by 3 again. It's like including another 3 in there. So that's the pattern. We keep taking away 3's. The equivalent of taking away 3's is putting a 3 in the denominator, right? When I divide by 3 like this, on the next step, I get 3. When I divide by 3 like this, I get a 1. When I divide by 3 again, then I divide by 3 again, and so on and so forth. Okay, it's the same thing for any number or variable. So if I did the same thing with a, right? A to the 1, a to the 2, a to the 3. Let's go a little lower and do a different. A to the 1. Oopsies. Let's just go a to the 1, a to the 2, a to the 3. A to the 0 is also equal to 1, right? Because I'm dividing by a, any number to the 0 power ends up being 1. Because if I start with a to the 1 and then divide by a to get to a to the 0, it cancels. And similarly, um, a to the negative 1 power is equal to 1 over a to the negative 2 power is equal to 1 over a squared, a to the negative 3 power is equal to 1 over a cubed. Or I'll say a times a times a. And for a squared, it's kind of like I'm dividing by a twice. So I have a times a like that too. So it works for any number and any variable like so. So what do I have the in general rule? So my new rules I'm having for myself is any x to the 0 power, doesn't matter what my base is, if it's to the 0 power, it's 1. Any x to the negative e power, whatever that e is, that can be a 5, 1,000, doesn't matter if it's negative, that's the same as 1 over x to the e as a fraction, right? That comes in the denominator. Okay, so let's do some tests here. Let's figure this out. It's true for any number of variables. So 1948, great year, I guess. Probably not really. What is that to the 0 power? Oh man, doesn't matter how big that number is. That's equal to 1. Oh, nice. Negative 9 to the 0 power. It's a negative number. Doesn't matter. It's to the 0 power. It's equal to 1. Negative 9 to the 0 power. I guess you're saying, oh, it's 1. Not the case here. Here, it's like saying their base is negative 9, and any base to a 0 power is 1. Here, it's saying negative 9 to the 0 power. It's almost like this is on its own thing. If we treated this as its own thing first, 9 to the 0 power is 1, and then I have a negative 1. So because the negative is not a part of the exponent, it's not a part of the base for the exponent, it's on the side here, negative 9 to the 0 power. That's negative 1 here. But if you have something else like 3 and x's, if they're in the exponent, or in the base for the exponent, excuse me, this still equals 1. And like before, even though these looks close to each other, this is really 3 times x to the 0 power. This is the stuff you do first. X to the 0 power is 1. 1 times 3, 3. There we go. Okay, so let's do this new kind of problem here. This will be the last problems for this video here. We'll do the negative exponent stuff later, I think, in another video. So a new kind of problem is when you have x to an a power to the b power. So you have like an exponent as your base, and then you have another exponent on top. It's like a stacking of exponents. They're like nested inside of each other. Don't you see, before we go, this looks different than, say, these problems. These problems had two things you're multiplying together, whereas this one has like one thing we're exponeting again. You might remember the rule, but again, we rely on the same thing we did before. We do when in doubt, write it out. So I'm going to write out this base thing to the 4 power. I have 7 squared times 7 squared times 7 squared times 7 squared. I don't care if this is a happy face. I don't care if it's 7 squared. I don't care if it's 1,000. If it's to the 4th power, I write it out 4 times. I write out 7 squared 4 times, and I know how to write out 7 squared as well. I can write each of these 7 squares to be 7 times 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 7. What is that? 1, 2, 3, 4, 5, 6, 7, 8. This is equal to 7 to the 8th power. Let's do it again. We have y to the 5th to the 3rd power. When in doubt, write it out. I see this to the 3rd power is y to the 5th times y to the 5th times y to the 5th. Okay? And each of these y to the 5ths, I'm going to have y times y times y times y times y, y times y times y times y times y, y times y times y times y times y. What do you know? That's a total of 15 y's when I write it out. So this is y to the 15th power. Now you might see the rule here. You might see, oh my gosh, I have y to the 15th. This is what? What was this? This was 5 to the 3rd power, like y to the 5th to the 3rd power. Really, it's like if I multiply these exponents, I get the answer. 5 times 3 is 15. If I multiply these two exponents, I get the answer. 2 times 4 is 8, so 7 to the 8th power. So in general, this is the rule. We multiply these exponents together, but we got to be careful. We got to be careful when we do stuff like this. Because if I had, let's leave this, let's put it as squared here. I don't know why I have it 3 made like that. If I have it like this, it's good to know that I can still write it out. So I'm going to write it out. I have this stuff to the 3rd power, so I have 3 times a squared times 3 times a squared times 3 times a squared, because I still have this 3 here, like so. And I can still split this up, right? This is a times a times a times a. And what is 3 times 3 times 3? That's 27, right? So this is 27 a to the 6th power, because I have 6 a's at the end here. That is because I changed this to a squared instead of an a. If it was just a, I would just have it a to the 3rd power here. But remember, when I have this 3, I don't just like leave it as 3a to the 6 like that. I'm still taking this 3 and multiplying it out 3 times as well, because it's a part of the exponents. We're a part of the base of the exponent. Excuse me. Keep making that subtle mistake here. So if you write out anything that's in your base this many times, you won't make any mistakes. So that's just a good thing to know here. Okay, so let's kind of recap on what the rules are, right? We had x to the a times x to the b is adding the exponents. X to the a over x to the b, so long as they're the same base, you're subtracting your exponents. X to the 0 is equal to 1, and x to the negative a power is equal to 1 over x to the a. Those, oh, and lastly, x to the a to the b power like this is x to the a times b. Those are all the rules we covered on this video. We'll do some more things with negative exponents in the next video, as well as some like extra practice at the end as well for like putting all the rules together, right? Thank you all for watching.